So I'm back. I hope you're all back. I hope you had a good spring break and that you all stayed healthy. So this is Tuesday, April 14th class. Just a couple of announcements here. The test on chapters 4 and 5 is on Thursday, so in 2 days, on the 16th. I'll talk about it a little bit later. I don't have a whole lot to say, but I'll talk about it a little bit later. You should already have gotten an email from me detailing the rules and how things are going to work for this test. Not a whole lot different from the last one. And there should be very specific comments in that email about deadlines, which will be strictly adhered to. So make sure you read it and understand what's going on with that. And the only other announcement is that the last day to withdraw is on Sunday the 26th. So be aware of that. I'll already have these tests graded and into the grading system, which I have uploaded onto Canvas, so you can see exactly where you stand so that you can make a more informed decision. I think that's my only announcements. We're gonna start chapter 6 today and see where it takes us. Nothing on today's lesson will be on the test on Thursday. So chapter 6 is not on that test on Thursday. So again, we're starting chapter 6, so let me get rid of those announcements and we'll go ahead and get started. So chapter 6 is about functions, composite functions, and then we get into inverse function, one-to-one functions, inverse functions, and from there we go to exponential functions and log functions. So that's sort of what a synopsis of chapter 6, what we're going to be dealing with. So the very first section, 6.1, is about these things called composite functions. This should be a review, at least the idea of a composite function and how you deal with it. What might be new is talking about how you find the domain of a composite function. So in the handout, I define again what a composite function is, or remind you what a composite function is. So given two functions, f of x, let's say, and g of x, a composite function would be, for example, f of g of x or g of f of x, which basically is putting one function into the other. So I define the idea of that composite function. One type of a composite function, if your two functions are f of x and g of x, is to do f of g of x. So this is red. There's this little sort of tiny little open circle here. It's red, f composed with g, or f of g of x. And what it means is f of g of x. In other words, I'm going to put g's function into f's function. And I know, and maybe you read that as fog. Sometimes I know in intermediate algebra they talk about fog or goff. I won't tend to read it that way. I'll read it as f of g of x, and I'll actually write it like this as opposed to like this. So when I see this is what I see in my head. And if it says goff, g little circle f of x, that means g of f of x, and I'll see it like that, and I'll write it like that on the board as well. Basically, again, what it's saying is we're putting one function into the other. That's what a composite function is. So in other words, if I told you that f of x was 3x plus 2 and g of x was 5, if I wanted to find f of g of x, in other words, the composite function, f composed of g, basically what I'm telling you to do is put whatever g of x is into f. If I told you that g of x was 5, then basically what we're trying to do here is to find f of 5. 5. In other words, I'm replacing g of x with what it's equal to, which is 5, and then I'm going to evaluate f at 5, so I would put 5 in here. And we know how to do that. So it's the same idea as evaluating a function at a given number, but now instead of a given number, we're going to evaluate it at whatever that other function is. In this case, it happened to be 5, and so I would just plug 5 in. And maybe that's just confusing the issue, so I'm going to erase this concrete example and simply state again that we're taking one function, whatever it is, and putting it into the other one. Sometimes it will be a number, and I'll just be evaluating a number. Other times it will be more complicated than a number. And we did that with the difference quotient. We took f of x, and then we figured out what f of x plus h was. So we're putting one function into another one. We just weren't calling it composite functions. So we've done this before. It isn't going to change how we do it. The only extra piece of information here is we're going to talk about the domain of a composite function. So notice it says the domain of f of g of x is the set of all numbers in the domain of g of x and in the domain of f of g of x. So in other words, when we're talking about the domain of a composite function, we're talking about the domain, the intersection, so see that word and, in the domain of g of x and in the domain of f of g of x. We're talking about the intersection, and means intersection, of the domain of g of x, the function that you're putting into the composite function. We're talking about the intersection of the domain of g of x with the domain of the composite function. In other words, the final answer. So we're talking about looking at two domains and intersecting them. We're talking about the domain of the function being put in to the composite function with the domain of the final simplification of the composite function. So intersection, or what they have in common, of the domain of the function being put in and the domain of the final answer. So let's take a look at these and see what we can do with them. I have basically 3 examples here that talk about finding the composite function and then finding the domain. So the directions say find f of g of x and g of f of x and state the domain of each one for problems number 1, 2, and 3. So let's take a look at problem number 1 and see what it is I want to do with them. So there's my 2 functions, f of x and g of x. They want me to find f of g of x and find the domain of that. And then they want me to find g of f of x and find the domain of that. So in order to figure out those composite functions and domains, keep in mind that I also need to know the domain of each one of these, because that's going to be part of the domain, of the way I find the domain for the answer of the composite function. So first thing I'm going to do before I even try to figure out f of g of x is think about the domain of each one of these. So let me tackle that first. So here's f of x. What would be the domain of f of x? So if this is f of x and I'm looking for domain, all possible x values, I'm talking about, are there any restrictions on x? Well, this is a fraction, which means there might be restrictions on x if there's x's in the denominator, and sure enough, there are. So I know some of you can just look at that and tell me, but if you're not sure, what are we talking about? So we're talking about denominators cannot equal 0. So basically my domain for f of x is coming from the idea of this x plus 3 can't equal 0, which means that x can't equal what value? -3. And I know if you can just jump to that, that's fine, but this is what's going on. So x can't equal -3. So my domain of f of x, the only restriction is that x can't equal -3. And it's fine to write it that way. Since they aren't asking for it specifically in interval notation, I'm just going to write it as to the restrictions. If they wanted interval notation, then I'd go negative infinity to negative 3, parenthesis, union, parenthesis, negative 3 to infinity. In other words, everything but negative 3. So there's the domain of f of x. I'm going to go figure out the domain of g of x as well, because again, it will play a part in terms of my composite function. So domain of g of x, I'm looking for restrictions on x. Sure enough, there's an x in the denominator, and this one's even easier. The denominator can't equal 0. The denominator is x, so I'm done. There's my domain of g of x. So domain of f of x, x can't be negative 3, everything but negative 3. Domain of g of x, everything but 0. So now I'm going to go, part A says, go find f of g of x. That's what they want me to figure out. F of g of x. So f, little circle, g of x. I'm going to write it like this because that's what it means. So f of g of x. So here's the deal. We're going to take g's function and put it into s. Some students got used to doing that in intermediate algebra and didn't have to rewrite this at all. I'm going to take this one step at a time. So I'm actually going to write what this means. This means f of, what is g of x? G of x is 2 over x. So I'm actually going to write that down so I know exactly what I'm putting into f. If you don't need this step, that's fine, but I'm going to always write it just to help those of you that are still struggling with this idea of a composite function. So f of g of x says take g's function and put it into f. So here's g's function, 2 over x, and I'm putting that into f. So now, tell me, if I asked you for what's f of 5, you'd say, oh, go to the f function and replace x with 5, right? And you'd put a 5 everywhere where you see an x. Or if I said, what's f of 3, you'd say, go to the f function and replace x with 3. So everywhere I see an x, there, and there, I would put a 3 in there. But this is everywhere you see an x in the f's function, replace it with what? Not the number 5 or the number 3, but replace it with a 2 over an x. So I'm going to take f's function, wherever I see an x here, I'm going to replace it with a 2 over x. So I'm going to write 2 over x for that x, over, and now I'm going to write for this x, 2 over x, and then I have a plus 3. So everywhere I saw an x, I replaced it with a 2 over x. And now I need, so this is f of g of x, but now I need to simplify that. It's a mess. So how do I simplify this? This is a complex fraction, so we're going back to chapter R. That chapter R and chapter 1 are going to haunt you if you did not learn them in the first place at the beginning of this class. How do I simplify this algebraically? I have two choices. I can either convert this into a single fraction, which it already is, and then convert these two terms into a single fraction, which they are not yet. So I could do that by getting a common denominator and then adding them and having a single fraction. And then I would have a single fraction over a single fraction, which would be the fraction on the top divided by the fraction on the bottom, which I could turn into the fraction on the top times the reciprocal of the fraction on the bottom. Or, since it's not a single fraction over a single fraction, instead I could just decide on the LCD for all the little single terms in this complex fraction and multiply every single one of them by whatever that LCD is. So I'm going to choose to do it that way. So I'm going to take every term, top and bottom, times the LCD, which I see is just x. So I'm going to take this term times x, this term times x, and this term times x. And that way I'll get rid of the complex fraction and turn it into a simple fraction. So this turns into, these x's cancel, which was the point, I get 2 in the numerator. The denominator, these x's cancel, which was the point, I get a 2, plus, nothing cancels here, so 3 times x is 3x. I just don't like the way this looks, so I'm going to rewrite it as 2 over, I'm going to put these terms in order, 3x plus 2. And now I'm going to try to simplify that simple fraction. The only way I can simplify this is to factor. If I can factor something in both the top and the bottom that's the same, then I can cancel them. The fact is there's only one term in the numerator. The denominator has 2 terms. Can I factor? So do not cancel those 2's. you have to be able to factor a 2 out of every term down here in order to be able to cancel 2's. And is there a GCF of a 2 down here? No. So guess what? This is simplified. This is as far as it goes. So this is f of g of x. This is the fog of x. So there's my answer for the first part, which is what's f of g of x. Now they want to know the domain of f of g of x. So the domain of f of g of x comes from the intersection of the domain of this f of g of x answer that we got that's simplified, but intersect that with the domain of what we put in, which is the g of x. So notice we put in a complexity to this composite function using the 2 over x, which means its domain is going to play a part as well. So it's not just the domain of your final answer, it's the intersection of the domain of what you put in. So it's the intersection of the domain of the g of x with the domain of my f of g of x. Okay, well, the domain of my g of x, we said the domain of g of x is x can't equal 0, x can't equal 0, and now we just have to look at the domain of this answer for my composite function. So tell me, this has a restriction as well. What value can x not be down here? With x can't equal, what would that have to be? Negative 2/3. X can't equal negative 2/3. So I need to do an intersection of these two restrictions on the domain, which means that this x can't be 0, this says x can't be negative 2/3, so it's all real numbers except for 0 and negative 2/3. So my domain of f of g of x is going to be x can't equal 0, x can't equal negative 2/3. So I intersected those two, and this is what I got. X can't be 0, x can't be negative 2/3. Interval notation for that is a little trickier. I'd have to go negative infinity to negative 2/3, parenthesis, union, parenthesis, negative 2/3 to 0, parenthesis, union, parenthesis, 0 to infinity. There's no point. Just list the restrictions. So there's f of g of x. They also want me to find g of f of x. So part B, what is g of f of x, or gof of x? So again, this is saying put f's function into g, or in other words, what is f of x? F of x is x over x plus 3. I'm going to put that into g's function wherever I see an x. So now I'm looking at g's function, I'm replacing x with this mess, x over x plus 3. So g's function says 2 over x, but instead of x, I'm going to put in x over x plus 3. So there's g of f of x, but it's not simplified yet. That's also a complex fraction, but this is a single fraction. 2 is like 2 over 1, over a single fraction, x over x plus 3. So this one, I don't have to multiply both top and bottom by the LCD, although I still feel like that's easier, but I know most students would prefer to do the division, which is the reciprocal of the, where you multiply by the reciprocal. So that means that this is 2 divided by x over x plus 3. So that means it's 2 times x plus 3 over x. This is like 2 over 1. And nothing can factor, no GCFs, nothing cancels. So the top is 2 times x plus 3. I'm not even going to multiply it because it's nicer to show that none of the factors have anything in common. Is it wrong if you wrote 2x plus 6 in the numerator? No, it's not wrong. But I'm just going to leave it factored to show that I tried to simplify and nothing canceled. So this is g of f of x. G of f of x simplified. So there's the first part of that one. The second part is they want to know the domain. So the domain of g of f of x comes from the intersection of the domain of, what did we put in this time? We put in f of x. So it comes from the intersection of the domain of f of x with the domain of the composite function. Well, the domain of f of x, what did we say the domain of f of x was? We said x can't equal -3. X can't equal -3, so that's this one, domain of f of x. And domain of the composite function simplified looks like this, and the denominator only has an x, so I can tell the domain of this simplified version is x can't equal 0. So now I'm going to intersect x can't be -3. So this is all real numbers except for -3. This is all real numbers except for 0. So the intersection of those two, I put the two together. We're basically saying all real numbers except for now -3 and 0. So my domain of g of f of x is going to be x can't equal -3, x can't equal 0 when I intersect those two. And again, this is the easiest way to write it, just listing the restrictions. If I were writing that in interval notation, I'd go -infinity to -3, parenthesis, union, -3 to 0, parenthesis, union, 0 to infinity. In other words, everything but 0 and -3. So there's the first composite function example done, and thinking about the domains. So let's take a look at number 2 and see what we can do with it. So there's my two functions, same questions. So they want me to figure out f of g of x and then g of f of x. I'm going to go figure out the domain of each one of these as well, because I know that's going to play a part in my final answer for the domain of the composite functions. So let's look at this one in terms of domain. So domain of f of x. So I'm looking for restrictions on x. I don't see any x's in denominators, but what I do see is an x underneath an even root. So it's in a square root, which means that I do have issues because I need to keep the answers real. So the radicand, if you recall, the radicand has to be greater than or equal to 0. The radicand in this case is x minus 2, has to be greater than or equal to 0. So what does that mean about x? X is going to have to be greater than or equal to, I add 2, so I get 2. So it looks like the domain of f of x is x has to be greater than or equal to 2. So in other words, bracket 2 to infinity. So there's that one. This one, the domain of g of x, I don't see any restrictions here. No x's in square roots, no x's in denominators. So domain of g of x is all real numbers. There we go. Okay, so there we have those two domains. So now I'm going to go find f of g of x. So I'm putting g into f. So in other words, f of g of x is 1 minus 2x. So f of 1 minus 2x. So I'm putting g into f. So here's f. So wherever I see an x, I'm going to replace it with 1 minus 2x. So this says the square root of x, which I'm replacing with 1 minus 2x, and then minus 2. So when I combine my terms here, I'm going to put them in good order, negative 2x and then minus 1. Can I simplify this? Well, is this a perfect square? I don't think so. And yeah, you can factor out a negative 1, but the negative 1 is still going to be in here, and I'm just going to leave it the way it is because there really isn't anything I can do with that. So this is f of g of x. As simplified as it gets. Now they want the domain of this. So the domain of f of g of x, the composite function, comes from, again, the intersection of the domain of, what did we put in? We put in the g of x intersection of the domain of g of x with the domain of this final simplified version of the composite function. Well, the domain of g of x, where's g of x? Was all real numbers. Oh, that's nice. And then I'm going to intersect that, which there's no restrictions there, with the domain of f of g of x. And here's what f of g of x looks like. So, are there any restrictions here? Well, again, I see a square root, an even root, and x is inside. So what I have to think about here is that the radicand has to be greater than or equal to 0. So that means negative 2x minus 1 needs to be greater than or equal to 0, and I need to go solve that. So that gives me negative 2x greater than or equal to 1, because I add 1. And then I'm going to divide by negative 2, and the minute I do that, what happens? Inequality changes, and this is x less than or equal to 1 divided by negative 2 is negative 1/2. So I am intersecting all real numbers with x has to be less than or equal to negative 1/2. So what do they have in common? X has to be less than or equal to negative 1/2. So my domain of f of g of x is going to be x less than or equal to negative 1/2. That's what needs to happen here. Or I could say negative infinity, comma, negative 1/2 bracket, if I wanted to do it in interval notation. So part B is, okay, go find g of f of x now. So put f into g. So in other words, g of f is the square root of x minus 2. So I'm putting f's function into g. So I'm going to look at g, and everywhere I see an x, I'm going to replace it with the square root of x minus 2. So that is 1 minus 2 times the square root of x minus 2. So 1 minus, and then 2 times x, but instead of x, I'm writing square root of x minus 2. And then I try to simplify that, and there's really not anything I can do here. These aren't like terms. This is as simple as this gets. So this is g of f of x. And now they want the domain. So again, the domain of g of f of x is equal to the intersection of the domain of what we put in, which is the f of x, with this final simplified version of the composite function. So the domain of f of x was x has to be greater than or equal to 2. And now I need to figure out this domain of the simplified version, and then I'll see what they have in common. Well, domain of the composite simplified function simplified version, there's nothing. Here's where the issue is again, and it's a square root, and this is the radicand. So basically, radicand has to be greater than or equal to 0, and the radicand is x minus 2 has to be greater than or equal to 0. This is the same thing, x greater than or equal to 2, right? So if I intersect x greater than or equal to 2 with x greater than or equal to 2, I'm going to get x is greater than or equal to 2. So my domain for the composite function is x greater than or equal to 2. So there's one more example here that we need to take a look at. So the same questions, they want me to find f of g of x, g of f of x, and the domain of each one. So before I do any of those composite functions, I'm going to go find the domain of each one of these, because again, that will play a part. This first one, I don't see any x's in denominators. I don't see any x's underneath even roots. So I'm thinking there's no restrictions. The domain is all real numbers. domain of g of x. So now I do see an x in a radicand, but it's a cube root. And are there issues with cube roots if the x happens to be negative? And because that's the issue with the even roots. If the x is negative under there, then we'll have imaginary numbers. But guess what? When it's an odd root, you can have negative numbers in the radicand, right? The cube root of negative 8 is negative 2. The cube root of negative 27 is negative 3. So there's no restrictions here. This is all real numbers. X can be anything, positive or negative, it doesn't matter. So that's nice. So there's my two domains of these guys. So now I'm going to go figure out f of g of x. So again, this is putting g's function into f. So in other words, what I'm evaluating here is f of g of x is the cube root of 2x. So anywhere, so I'm going to go to s function, and anywhere I see an x, I'm going to replace it with the cube root of 2x. So let's see, I have a 1/2 multiplying with x, which is being replaced with the cube root of 2x, and then I'm going to cube that x. So here's the x cubed, but instead of x, I'm writing cube root of 2x. And now I'm going to try and simplify this. That 1/2 is not being cubed, just the expression of the x is being cubed. So what happens when you cube a cube root? You're left with the radicand, which is 2x. So this says 1/2 times 2x. And I can cancel here, so this just gives me x. So f of g of x equals x. This actually is a special kind of composite function that we'll talk about it in the next section. But anyway, that was kind of nice that it all canceled out and got me back to x. They want the domain of f of g of x as well. And that comes from the intersection of the domain of what we put in, which is g of x, with the domain of the composite function simplified version, f of g of x. Well, the domain of g of x was all real numbers, and the domain of f of g of x simplified version was all real numbers. And if I intersect all real numbers with all real numbers, I get all real numbers. There are no restrictions. So now I'll go do g of f of x. So the second part of this, g of f of x, that says take g's function and replace x with f's function. So f of x is that 1/2 x cubed. So I'm going to put 1/2 x cubed into g's function wherever I see an x. Well, g's function says cube root of 2 multiplying with x, but in place of the x, I'm going to put in 1/2 x cubed. So cube root of 2 times x, where x is being replaced with 1/2 x cubed, and I'm going to simplify it. Well, this says the cube root of, when I take 2 times 1/2 times x cubed, the 2's cancel, and I just get x cubed in here. And the cube root of x cubed is x. That's kind of fun. Both composite functions, they sort of undid each other, and they ended up just with an x. Kind of like if you take an x, add 2, and then subtract 2, you'll be back at the x. So here's g of f of x. They also want to know the domain of g of f of x. And again, that domain is coming from the intersection of the domain of what you put in, which was the f of x, with the domain of the final simplified version of the composite function. Well, the domain of f of x, we said, is all real numbers. The domain of the simplified complex composite function, the domain of x is just all real numbers. There's no restrictions there. So when I intersect all real numbers with all real numbers, I get all real numbers for my final answer for the domain of the composite function g of f of x. So a nice, hopefully review of composite functions and also looking at their domains. There's 2 more questions here, 2 more examples. Then just sort of play around with things a little bit and make sure you really understand what's going on. So number 4 says, hey, if I tell you that I have some function called h of x and it's equal to x squared plus 1 all cubed, can you define f of x and g of x in a way that f of g of x, in other words, if I put g into f, this one into this one, I will get this function right here. I will get x squared plus 1 cubed. So that's what this question is saying. They told me what h of x was, just so they could tell me what it was. And then they said, if you put g into f, if you do f of g of x, they want you to get that answer. So this is just, again, trying to get you to understand that when you do fog, f of g of x, you're putting one function into another one. So when I look at this, I can kind of see going inside out a function in another one. See that x squared plus 1? It's been put in something that says to cube it. And so if you can look at it inside out, you can kind of see how to define these, or at least an easy way of how to define these. There are different answers here, but the most obvious one is that we took x squared plus 1 and we put it into something that was cubed. So I think the x squared plus 1 is going to be the function I'm going to put in. So I'm going to try this. I'm going to let that g of x be the x squared plus 1. And then I'm putting it into something that's been cubed. So guess what? F of x would just be x cubed. So think about this. You're putting this into this wherever you see an x. So you replace x with x squared plus 1 and you get x squared plus 1 cubed. And so that would be my answer to that one. So it's, again, just looking at the idea of putting one function into another one. And then the last example here, number 5, is a short section. Tells us that f of x is this big long thing. And then g of x is equal to 1. And they want me to find f of g of x and g of f of x. So they don't want to bother to find domains. They just want me to find f of g of x and then g of f of x. All right, so let's do that. First one, f of g of x. So again, I always write it this way because it really spells out to me which function's going into which one. So f of g of x, that's the fog. And again, if you want to, you don't have to do this, but I find it helps some students. This is saying f of, what is g of x? G of x is 1. So whatever g of x is, put it in here. And now what you're doing is you're evaluating f at 1. We know how to do this. F at 1 just says replace x with 1. Boy, this was nice. I like how they did this. So I'm just going to put 1 in there. 2 times 1 cubed minus 4 times 1 squared plus 2 times 1 minus 3. That gives me 2 minus 4 plus 2 minus 3. That gives me negative 3. So f of g of x actually ended up just being a number, negative 3. That was nice. B says do it the other way around. Or the second question here says find g of f of x, so goff. Again, I read it like this, so it really spells out to me what's going into what. And again, you can even do this. What is f of x? F of x is 2x cubed minus 4x squared plus 2x minus 3. I'm putting this function f into g, wherever I see an x. So here's g's function right here. Wherever I see an x, I'm going to replace it with this. So I start to write down g's function, waiting for the x to happen to replace it with this, and it never happens. There is no x here for me to replace it with this monster. So guess what? G of f of x is just going to equal 1. There's nothing to replace. So just, just really playing a little bit with you, trying to trick you. That's what's going on with this one. Just, again, following the rules, putting the one into the other, and seeing what happens when you simplify it. So that's 6.1, just sort of a quick review of composite functions. We're going to move on to 6.2 and see what we can do with it. Get rid of this. So 6.2 is all about what's called one-to-one functions and then inverse functions. So I defined a one-to-one function, and we usually write it like this with a 1-1, which I wrote right underneath that. So a one-to-one function. So let me read what this says for a minute. It says to be a one-to-one function, each x value corresponds to only one y value. That sounds familiar. Remember? Same x can't be paired with different y's. That's what makes something a function, right? So same x can't be paired with different y's. Same x value can't be paired with different y values. That's what makes something a function in the first place. What kind of test do we do for that? If we had a graph, vertical line test, okay. But then there's more, and then it says, and each y value corresponds to only one x value. So what have we done here? So remember, to be a function, we just couldn't have same x's paired with different y's. It had to pass that vertical line test, so we couldn't have same x's paired with different y's. But now we're saying to be a one-to-one function, not only can the same x not be paired with different y's, but also the same y can't be paired with different x's. So now it's fair. It goes both ways. So also, to be one-to-one, the same y can't be paired with different x's. So function, same x can't be paired with different y's, and that's all. But to be a one-to-one function, it has to go both ways. Same x can't be paired with different y's, same y can't be paired with different x's. And what do you suppose the test is to see if same y can't be paired with different x's? Horizontal line test. If you hit more than one point with a horizontal line test, then it fails this idea where the same y can't be paired with different x's. So this would be a horizontal line test that will help us with that if we have a graph. So to have a function, same x can't be paired with different y's only. To have a one-to-one function, it has to go both ways. Same x can't be paired with different y's, and the same y cannot be paired with different x's. So they each have one and only one x or y value to go with them. So it goes in both directions. So the next two questions are, can you tell if these functions are one-to-one or not? And notice I don't have a graph of them. I just have the algebraic expression of these functions. We're going to look at it algebraically, and then we're going to take a peek at the graph as well, just to give you a visual. So they want to know if they're one-to-one. Well, first of all, to be a one-to-one function, it's going to have to be a function to start with, because clearly to be one-to-one, we have to have that idea. Same x can't be paired with different y's. But that's not enough to be one-to-one. It has to go in the other direction as well. So the first thing I'm going to do is show algebraically that this is a function, this idea, same x can't be paired with different y's. And then I'm going to go try and show this idea where the same y can't be paired with different x's. And then I'll conclude, hopefully, that it's one-to-one, or I'll say that it's not because it fails one of those. So actually, the first thing I'm going to do is write this as y equals negative 3x plus 4, because I'm not dealing with the graph at the moment. I'm looking at it algebraically, which means that I need to think about plugging in an x value and seeing how many different answers I will get for y. If I plug in one x value, then I need to only get one y value out of it. If I get more than one y value out of it, then it's not even a function, let alone a one-to-one function, so I would say no. But how do I do that? I just have to think about if I put in one x value, I get how many y values? If I just get one y value, then so far it's a function. I just haven't shown that it's one-to-one yet. The fact that it's solved for y is the place I want it to be for me to think about whether it's a function or not. So if I put in one x value, so if I put in an input right here, how many answers will I get for y? If I put in one x value, I'm only going to get one y value. I get one y value. Okay, that says, hey, we have a function. But is it one-to-one? So how do I decide if it's one-to-one? What I have to do now, I have to go the other way around. If I put in a y value, I want to input a y and see if I only get one x. Well, in order to input a y, it's useful for me to take this and solve it for x. Put the y over in the input spot and put the x over here. So I'm going to now solve for x. So let's see, y equals negative 3x plus 4. I'll subtract 4. So I'll have y minus 4 equals negative 3x. I'll divide every term by negative 3. I'm going to write my x first because it's easier to read. X equals, this is negative 1/3 y. And this is going to turn into plus 4/3. So here it is solved for x now. So now, if I put in one y values, in other words, I'm looking at input, I get how many x values? So I'm trying to put in a y and see if I'm going to get more than one x, because if I do, it's not one-to-one. So if I put in one y value here, how many answers will I get for x? Exactly one. I get one x value. So what does that mean? Well, it was already past this condition, which made it a function, and now it's past this condition, which means that yes, this is a one-to-one function because it passed both of these conditions, looking at the input and the output. So that's the algebraic process of seeing if something is a one-to-one function. The easier way, if I can do it, is to look at the graph. And honestly, so here's the visual or the graph. I can actually graph this without even being ridiculously accurate. In other words, I'm not even going to put it on an XY axis. First of all, you should know that this is what? What's this the graph of? It's linear, so it's a line. And the question in my mind is it vertical, which would be an issue? Is it horizontal, which would now be an issue for a one-to-one function? Or is it, falling as I go from left to right, or rising as I go from left to right? So all I have to do here is look at the slope. The slope is -3, which means that this guy is doing what? Falling as I go left to right. So I'm not even going to do it accurately. The fact is, it looks something like that, which means, does it pass the vertical line test? Yes. Does it pass the horizontal line test now? Yes. So since it passes both vertical, which would be for a function, and horizontal, which would now be for, is it a one-to-one function, line tests, therefore it is, yes, it is a one-to-one function. And so I can pretty quickly look at the graph and answer that question. So the second one, same idea. They want me to decide if this equation is a one-to-one function. And it says f of x equals x squared plus 1. So doing this algebraically and not peeking at a graph, basically what I need to think about is, again, I'm going to write this as y equals x squared plus 1 to help myself out a little bit. If I put in one x value, I get, so will I get one y value? If I put one x value in there and evaluate this, how many answers am I going to get for y? Just one. I get one y value. Okay, so this is for a function. Same x can't be paired with different y's. So this works. So this is a function, but is it one-to-one? That's what the question is, which means I now have to test it in reverse. So to test it in reverse, in other words, I want to put in a y value and see how many answers I'll get for x when I do that. That means I need to take this and solve it for x. Solve for x. So y equals x squared plus 1, and then we'll do the input of the y value. So I'll subtract 1 from both sides. I get y minus 1 equals x squared. But now to solve this for x, I need to do the square root property. So plus or minus the square root of this side. I'm going to write the x first. So square root of x squared is x. And over here I have plus or minus the square root of y minus 1. So here it is, solve for x. So now I'm going to think about if I put in one y value, I get how many x values? So if I put one y value in there and I evaluate this, how many answers am I going to get for x? 2. I get 2 x values. What is that saying? That's saying same y value is paired with 2 different x values, which in the past didn't make a difference for a function, but now it does make a difference for a one-to-one function. So no, not one-to-one. So it's not a one-to-one function. It's a function, but it's not one-to-one. The rule doesn't work both ways. And if I want to look at the visual here, or the graph, we should know what this is a graph of as well. So this is our base function, y equals x squared. What does y equals x squared look like? Right side up parabola, vertex at 0, 0, right? Base function. Has it gotten skinnier or wider? No, because I didn't change the coefficient of the x squared. Has it moved? So I'll keep it the same width. Has it moved to the left or to the right? No, because I didn't change the x to an x plus something or x minus something. But what did I do? I added 1, so it moves what? 1 up. Just the y value gets changed, right? So this is basically a right side up parabola. It's just emanating not from 0, 0, but from 0, 1. So I'm not even going to put it on an xy axis because I know more or less what it looks like. And now I'm going to do vertical line test and horizontal line test. So vertical line test, does it pass it? It does, which means it's a function, which is what we saw. It is a function. Yes, passes. Passes, which means only that it's a function. Doesn't say anything about whether it's one-to-one or not. To be a one-to-one function, we now have to look at the horizontal line test. And the horizontal line test, it fails all over the place. It hits more than one place, so it fails. And since it fails this, it means it is not one-to-one. So it is a function, but it's not a one-to-one function. So there's some examples and descriptions of what makes a one-to-one function. Now we're going to talk about an inverse function, which uses this definition of a one-to-one function. So underneath inverse function, it says for f of x, a function, to have an inverse, which is written as, oh, look at that, an f with a -1 and then an x. I'll talk about that in a second. It says that that original function, f of x, needs to be one-to-one. So what that's saying is, first of all, for a function to have what's called an inverse function, the original function needs to be one-to-one. So it needs to pass vertical and horizontal line test. Or in other words, same x can't be paired with different y's, and the same y cannot be paired with different x's. But then it also says, since if a function is 1-to-1, it has an inverse, and if you can figure out what the inverse is, number 1 says, if you take f of g of x, which we're saying is the inverse, you should get x. And if you do it the other way around, g of f of x, you should get x for every x in the domain of each one of those. So think about that for a second. Remember that one example we did, number 3 in the last section, where we did f of g of x and g of f of x and we got x? Those were inverse functions of each other. That's what happens when they're inverses. Inverse functions kind of undo each other. Like, you know, I have x plus 2 and then I subtract 2, or I have x times 2 and then I divide by 2. I get back to my original x. And that's what's going on with inverse functions. But again, to have an inverse function, the original function must be 1-to-1. And if it is, then it has an inverse and we should be able to figure it out. And if we did the composite f of g of x and g of f of x, we would get x. They would undo each other when I put one into the other. Interesting. So let me look at that notation for a minute of that inverse function. So an inverse function is written f with a little negative 1 of x. And I want to comment here, this is not a power. In this context, this is saying f inverse of x. And I think I wrote down how it's read. No, I did not. So this is read f inverse of x. This means an inverse function has nothing, it's not a power. That does not mean 1 over f of x. Okay, so it's not a power, it's a different notation and has a different connotation, and it means that we're talking about an inverse function. That's all we're talking about, an inverse function, when we write f with a little negative 1 and an x. And it's read f inverse of x. And the fact is, for f of x to have an inverse, it needs to be 1-to-1. So f of x must be 1-to-1 to have an inverse. And the fact is if it has an inverse, then if I take f of its inverse, I'll get x. And if I take g of and if I take g of f of x, in other words, its inverse, and put the f into it, I'll get x. So f of x must be 1-to-1 to have an inverse. Let's call it g of x instead of f inverse of x. And the fact is if f of x and g of x are inverses, then this should hold. When I put one inside of the other in both directions, I should end up with x. So let's go try something here. My next two examples are, I'm asking if f of x and g of x are actually inverse functions. So let's go see what we can do with those. So I wrote down the first function, and then I thought, well, it sounds like inverse functions that they undo each other. Maybe g of x would be an inverse function to this one if I thought about kind of reversing the 2x, and then I thought about reversing the plus 5, so I wrote down minus 5. This is not a good way to come up with an equation of an inverse function to another function, but based on what we've sort of discussed, that one undoing the other, I thought I'd try it. So here's f of x, here's g of x, and I'm asking are they inverse functions of each other? So first of all, for f of x, my original function, to have an inverse, it needs to be 1 to 1. If this is not 1 to 1, then I don't even need to look at that and decide if it's its inverse or not by doing the f of g of x and the g of f of x. I can just say, hey, that's not 1 to 1, so it's not going to have an inverse, and I'm all done. So first thing first, so is this the inverse function of this? So that's the question here. Is g of x the f inverse of x? In other words, is it f's inverse? So first I need to think about is, so step A, is f of x a 1-to-1 function? Because if it's not, it does not have an inverse, and I'm done. So clearly if it doesn't have an inverse, then that can't be its inverse. So is it 1 to 1? So to be 1 to 1, it has to either algebraically look at 1x with 1y and 1y with 1x, or graphically, can I show passes vertical and horizontal line tests? So I'm going to go the easier route here, and I'm going to, because they haven't told me that I have to do it one way or another. So I'm just going to go look at the graph of this. So this is linear, right? And what kind of a line is this? Is it horizontal? Is it vertical? Is it horizontal? Is it following from left to right, or decreasing, or is it increasing from left to right? Looks to me like it is increasing from left to right because it has a positive slope. So this is f of x, more or less, and it passes vertical and horizontal line test. So is it 1 to 1? Yes. All right, so if it's 1 to 1, that means it has an inverse. So maybe this is its inverse. So how am I going to tell if this is its inverse or not for sure? I'm going to, so since it's 1 to 1, so f of x has an inverse function. Question is this it? Well, in order to figure out if that's it or not, I need to figure out f of g of x. And then I need to figure out g of f of x, and they both need to equal x. So let's try this one. This says put g into f. So in other words, f of g of x is 1/2 x minus 5. So I'm putting g of x into f. So here's f. Everywhere I see an x, I'm going to replace it with this. So this says 2 times x, which is 1/2 x minus 5, and then add 5. Well, when I try to simplify this, I can distribute this 2, and I get x minus 10 plus 5. That gives me x minus 5. Well, that's not x. So I can already say, no, g of x is not its inverse. No. But for practice, or maybe just to make sure I didn't make a mistake on this one, let's do it the other way around, g of f of x. So g of f of x means take g, put f into it. F is 2x plus 5. So there's f of x. So I'm going to put that into g. So g says 1/2 times x. So I replace x with 2x plus 5. And then subtract 5. So let's see. I take 1/2 times 2x, I get x. Take 1/2 times 5, I get 5 halves. Minus 5. So this isn't going to work either, which is good. I just want to make sure I hadn't made a mistake. So this gives me x, but it doesn't just give me x. It gives me 5 halves minus 10 halves, which is negative 5 halves. So that constant is an issue, which is not equal to x. So I stand by this answer. No, g of x is not its inverse. So I thought, darn, I thought that might work, where I just sort of reversed every little piece in the original function, but clearly it didn't work. So then I played around again and came up with example number 2, but I'm going to tell you I really didn't play around. There's a way to do this, and it's not by playing around. We'll talk about it shortly. So the second one, I said, all right, let me try this again. Let me manipulate g of x one more time and see if it's the inverse to 2x plus 5, because I sort of saw what was going on here when I did the f of g of x and g of f of x. Really not. I did, but that's not how I did it. And so I said, okay, number 2, f of x is 2x plus 5, and now I'm going to say g of x is 1/2 x minus 5/2. Because I saw the issue here wasn't so much with the 1/2 x, but it was with the constant. So, and now, same question. Now is g of x f's inverse? So again, to decide if f of x has an inverse, I need to show it's 1-to-1. So step A, is f of x a 1-to-1 function? And we said yes, right? Passes vertical and horizontal line test. Step B then and C are the two composite functions. If I do f of g of x and if I do g of f of x, will I get x? So here we go. F of g of x, f of now g of x is 1/2 x minus 5/2. So I'm going to put g into f wherever I see an x. So 2, here's my x, 1/2 x minus 5/2, and then add 5. So now when I distribute the 2, I get my x like I kept doing in the other one, and now look what happens. When I take 2 times the negative 5/2, the 2's cancel, I get negative 5, and then I add plus 5, and there it is, x. So now let me do g of f of x and make sure I still get x. So part C, I'll do g of f of x. So g of, I'm going to put f, which is 2x plus 5, into g. So g says 1/2 times x, so instead of x, I'm going to write 2x plus 5, and then minus 5/2. So now I distribute, and again I get my x here, which I did the last time too, and look what happens. 1/2 times 5 gives me positive 5/2. I have a negative 5/2, and I end up with x. So both times, f of g of x and g of f of x, I got x, which means that, yes, g of x is the inverse of f of x. Or in other words, f inverse of x is 1/2 x minus 5/2. If this is f of x, this is its inverse. So we proved it with the algebraic proof of is it the inverse function. So what I'd like to do now is, since we finally found what that inverse function was, I would actually like to look at the graph of both of these functions, the f of x and its inverse, and see what they look like on an xy axis. And before you peek at those 3 little comments, let's actually do the graph together, and we'll realize those comments happening as we do it, hopefully. So let me get rid of this. So I'm going to graph f of x equals 2x plus 5. And then I'm going to graph, and I'll do it in green, the inverse function, which was f inverse of x was equal to 1/2 x minus 5/2. I'm going to put them both on the same piece of graph paper. And I'm actually, instead of graphing this with a slope and an intercept, which I could certainly do, I would actually like to make a list of those points that I would be putting dots on. So I'm going to make a little t-table here because I would like to compare this t-table with that one when I'm done. So I'm going to start with, and I think I've decided to start with the extreme here, as if you're doing it the other way, if you're getting the slope and the y-intercept and you're filling in all the points all along 10 by 10 xy axis here, I'm going to start with 2, and when x is 2, the y value would be 9, and when x is, I'm going to go backwards because that's as high as we can go. If I let x be 3, then I'm off the piece of graph paper that I gave you. So then I'm going to let x be 1, and when x is 1, I get 7. When x is 0, I get 5. When x is -1, I get 3. When x is -2, I get 1. When x is -3, basically it's just the slope. I'm counting down by 2's here. When x is -3, because the slope is 2 to 1. When x is -3, I get -1. When x is -4, I get -3. When x is -5, I get -5, etc. And I'm going to graph that. And you, even if you graphed it the other way, you should see these ordered pairs coming up on your little dots. So I've got 2, 9, I'm going to try and make this look reasonable. So I've got 2, 9, which is right about there, and then I have 1, 7, which is right about there, and then I have 0, 5, which is there, and I have -1, 3, which is there, and -2, 1, which is there, and then -3 and -1, which is there. So basically we're counting 2 down, 1 to the left, or 2 up, 1 to the right. Then I have -4, -3, which is right around here, and -5, -5, right around here. And so here's f of x. Let's see if I can actually hit all my points when I draw my straight line. So this is f of x. A little crooked, unfortunately. So now I'm going to go do what we proved to be f inverse, which is this guy right here. And I'm going to make a t-table for this one as well. And I'm going to comment, this one's a little harder to do with the slope and the y-intercept because the y-intercept is a fraction. So I'd have to start at 0, -2.5. So I'd be in between boxes and then count 1 up and 2 to the right. And so it becomes a little more difficult. So instead, I'm going to pick some values here on my t-table. And in fact, I'm going to start at the extreme, and I'm going to start at 9. And I'm going to put 9 in here. So in other words, I'm trying to pick values that I won't end up with a fractional answer. And look at what happens when I put 9 in there. If I take 1/2 times 9, I get 9 halves. But 9 halves minus 5 halves is 4 halves. And 4 over 2 simplifies to 2. That was a good pick on my part. So now I'm going to go pick the value of 7, because I think this pattern might work. If I let x be 7, 1/2 times 7 is 7 halves, and 7 halves minus 5 halves is 2 halves, and 2 over 2 is 1. Huh. And now I'm going to guess, you know what number I'm going to pick next? I might have heard some of them. I think I heard you say 5. And if I pick 5, 1/2 times 5 is 5 halves, and 5 halves minus 5 halves is 0. And what's my next number that I'm going to pick? I'm going to pick 3. And can you tell me what the answer is without evaluating it? So have you seen the pattern? Look, 9, 2, 7, 1, 5, 0. What do you think the answer to this is going to be? I think it's going to be -1. If I put 3 in there, 3 halves minus 5 halves is -2 halves, which is -1. And in fact, the next ordered pair would be 1, -2. And the next one would be -1, -3. And the next one would be -3, -4. And the next one would be -5, -5, etc., etc., etc. The fact is that inverse functions, the x and the y values, have been exchanged. And you'll notice that that's what number 1 says. Notice that the x and the y values have been exchanged. So when I graph this, I've got 9, 2, which is right about there. And then I've got 7, 1, which is right about there. And then 5, 0, which is right about there, and then I've got 3, -1 there, and 1, -2, and then -1, -3, and -3, -4, and -5, -5. Off here. And this line, its inverse function, my lines are wavery. This is f inverse of x. So what have we noticed here? We've noticed that the x and y values have been exchanged. What else we will notice is that if the x and the y values have been exchanged, then the domain and the range should be exchanged. And that's what number 2 says. So let me look at this for the black function, domain and range. So in other words, for f of x. What's the domain of f of x? Left to right, -infinity to positive infinity, right? -infinity to positive infinity. What's the range of f of x, the black line? -infinity to positive infinity. These are boring. So let's look at the green line now, f inverse, domain and range. What's the domain of this green line, f inverse, -infinity to positive infinity, -infinity to positive infinity. What's the range of the green line? -infinity to positive infinity. The fact is that this should be that guy and this should be that guy, and the fact that they're all -infinity to infinity is what makes them boring, and so you can't really tell if that's what's happened, but that is what's happened when you exchange x and y's. And in addition to that, comment number 3 says, notice that the two graphs, f and f inverse, are symmetric to the line y equals x. So the line y equals x, do you remember what that looks like? That was a base function. That was that line that cuts quadrant 1 and quadrant 3 in half. And so I'm going to draw with a dotted line. And if you draw y equals x here, you should find that if you fold your paper on y equals x, the green should overlap with the black everywhere. Everywhere where it's folded and lapping over, they should go right on top of each other. That will always be the case. So 3 nice things about inverse functions. So now we're going to flip to the back side of this paper, where we actually have a couple of examples of where they want me to graph the function and then decide if it has an inverse. And if it does, then graph it, find the domain or range for both of them, and write the equation of the inverse. So you'll notice at the very top, I tell you how to write the equation of an equation's inverse, because we don't want to play around and play with it until we can get the right answer. There is actually a way to do it. And before I tell you what that way is, before I read those, I actually want to get started on example number 1 and show you that you can actually do almost all of example 1 without even knowing the equation of the inverse, based on the 3 facts that we just talked about with inverses. So let's go look at that first one. So they want me to graph this one, and then they want me to talk about its domain and range and decide if it has an inverse. And if it does, then they want me to graph its inverse, find its domain and range, and write its equation. So first I'll just work on this and get it graphed and decide if it even has an inverse, because if it doesn't have an inverse, then I don't have to do the rest of the problem. So I'm going to graph this guy, and I think as I graph this guy, just in case if it has an inverse, I'm going to make a t-table for it, because then I can just exchange the values of x and y. But we should know what this one looks like. This is the vertical snake, y equals x cubed, this guy, the base function. Moved what? Up 1, right? The y value is going to be affected by 1. So if it was y equals x cubed, we basically, for our values, we picked 0, and when x was 0, the y was 0, but now the y value is going to be 1, right? If you plug 0 in there and add 1. We picked 1 and negative 1 when we did y equals x cubed, and when it was 1, y was 1, but now y is going to be 2, one more. And when x was negative 1, the y was negative 1, but then I'm going to move it up 1, so it's going to become 0. I'm going to go with 2 and negative 2 as well. So when y was 2, we got, when x was 2, we got y was 8, but now it's going to be 1 up, so it's going to be 9. And when x was negative 2, we got negative 8, but now it's going to move 1 up, so it's going to be negative 7. So I'm going to go graph this one. I've got 0, 1 instead of 0, 0, 1, 2 instead of 1, 1. Oh, I got to get up to 9 here, so let me make sure I can get up to 9. So I've got 0, 1, and I've got 1, 2, and negative 1, 0, and 2, 9, and then negative 2, negative 7. So this is the vertical snake, just moved up 1. So it looks something like that. So here's f of x, a vertical snake, and you've got graph paper, so yours hopefully looks nicer than mine. There's that vertical snake, just adjusted and moved up 1. So the next question is, what's its domain and range? And is it 1 to 1? Because if it's 1 to 1, then it has an inverse, and they want me to continue. Well, the domain of this guy is negative infinity to positive infinity. We've done all this before when we did the base function. The range is negative infinity to positive infinity. Boring again. Okay. And is it 1 to 1? Is it a 1-to-1 function? So I've got the graph. Does it pass the vertical line test? Yes. Does it pass the horizontal line test? Yes. So is it 1 to 1? Yes. And if it's 1 to 1, then that means it has an inverse. So that means I need to continue. So it has an inverse. Has an inverse. So that means the inverse function, f inverse of x, I don't know what it's equal to yet. I haven't figured out how to write the equation of it yet. But I can tell you what it looks like. I can graph it, I can make its t-table, I can talk about its domain and range, all without having the equation. Interestingly enough, because what do we know about inverse functions? The x and y values have been reversed. So my t-table for f inverse is going to have a 1 and a 0, and then a 2 and a 1, a 0, negative 1, a 9, 2, and a negative 7, negative 2. The x's and the y's have just been exchanged. So, and I can graph that. So I've got 1, 0, I've got 2, 1, I have 0, negative 1, I have 9, 2, 9, 2, and I have negative 7, negative 2. So it's the horizontal snake sort of emanating from the 0, negative 1. So there's f inverse. There's its graph. Not only that, I can double check and make sure that there's symmetry going on here. Take a look at this, y equals x. I can see that symmetry, pretty graph, I like this one. If you fold it on y equals x, everything overlaps, the green and the black. I can talk about domain and range here, domain and range. So the green function, green, f inverse, domain, negative infinity to positive infinity. So I'm not peeking over here. I'll compare them in a minute. I'm just looking at my graph. Range of the green function, negative infinity to positive infinity. If I've done things right, this range should be that guy's domain, and this domain should be that guy's range. Well, yeah, they're all the same, so yes, that holds. The only thing left to this problem is, what's the equation of f inverse? I've got everything else answered. I just haven't figured out the equation of the inverse function. So how do you figure out the equation of an inverse function? So equation of f inverse. That's what I've got to think about. Well, here's where I'm going to look at those two steps at the very top. It says that if you want to write the equation of an equation's inverse, again reminding you that it has to be 1-to-1, otherwise it does not have an inverse, you're going to exchange the x and the y variables in the original equation, which then will be an equation that defines the inverse function implicitly. In other words, it won't be solved for y anymore. So look at this. The original equation is y equals x cubed plus 1. So I'm going to exchange x and y. So I'm going to write x equals y cubed plus 1. So this is an equation that represents or defines the inverse function implicitly because it hasn't been solved for y yet. See, here it was solved for y, but then I exchanged the x's and the y's, so now it's not solved for y anymore. So step 2 is take it and solve it for y, so we get what's called the explicit form of the inverse. And then it also says make sure you carry over any restrictions on the variables. We didn't have any restrictions on this original equation, so we have no restrictions to worry about. I need to solve for y. Solve for y. So I'll subtract 1. So I get x minus 1 equals y cubed. And then I'm going to take the cube root of both sides. And when I take a cube root, I do not introduce a plus or a minus. Cube roots just give one, they don't give both positive and negative answers, they just give positive answers. So I'm going to take the cube root of this side and the cube root of this side. I'm going to write my y first so it looks nicer. Y equals cube root of x minus 1. This is f inverse. So now I'm going to write down that equation up here where I had a big old question mark. So I'm going to write, f inverse's equation. So notice I do that last. F inverse's equation is f inverse equals the cube root of x minus 1. And now, one more thing to double check that everything works and is the way it should be. See that t-table? It better fit the equation that you just came up with. In other words, when x is 1, you get 0 for y. If x is 1, 1 minus 1 is 0, cube root of 0 is 0. When x is 2, 2 minus 1 is 1, cube root of 1 is 1. When x is 0, 0 minus 1 is negative 1. The cube root of negative 1 is negative 1. When x is 9, 9 minus 1 is 8, cube root of 8 is 2. When x is negative 7, negative 7 minus 1 is negative 8. The cube root of negative 8 is negative 2. So now that's my triple check to make sure that this all works the way I'm expecting it to work with inverse functions. So we have one more example in this section to take a look at. So let's go see what that one says. So it's the same directions. So they want me to, again, graph this, find its domain and range, decide if it's 1-to-1, and if it is, then it has an inverse. If it's not, then I'm done because it doesn't have an inverse. So I'm going to take this guy and I'm going to take a peek at its graph and decide. But notice this is a little different. This one says f of x equals x squared plus 1, but then they've added this extra condition on x, and they said x needs to be greater than or equal to 0. Why did they do that? Is that what that's talking about when make sure if there's a restriction that you carry it through when you're trying to find the equation of the inverse? I think maybe. So I'm going to take a look at this. I'm going to do a t-table again because I know to do the inverse all I have to do is switch the ordered pairs around. This is the base function, right? Y equals x squared moved up 1. So I think I can get his t-table But notice what they're saying here. So again, just lightly, this guy would be like this, right? Y equals x squared plus 1. But what have they told me? Well, first of all, take a look at this. If I didn't have this condition right here, is that a one-to-one function? You see a bunch of heads shaking no, so that's good. That's not one-to-one, is it? It fails the horizontal line test, which means it doesn't have an inverse. So if they didn't have this condition here, I would graph y equals x squared plus 1 and get something that looks like that. I would say the domain is negative infinity to infinity, and the range is 1 to infinity. And then for 1 to 1, I would say no, and I'd be done. Because if it's not 1 to 1, it does not have an inverse. But this isn't what they're asking for. They're saying, oh, but I only want x greater than or equal to 0. So which piece of this parabola do they want? They really only want that piece right there, right? X greater than or equal to 0 would be this side. And now is that 1 to 1? I think maybe it is. So that's why they've done that. They're trying to make it 1 to 1. Otherwise it wouldn't have been, and we would have been done early. So let's go do this now. I'll graph it nicer. So I'll make my t-table respecting this. So bigger, 0 or bigger. So 0, 1, 2, 3. Those are the only 4, 5, etc. So this is the base function moved up 1. So when x was 0, y was 0, but now it's going to be 1. When x was 1, y was 1, but now it's going to be 2. When x was 2, y was 4, but now it's going to be 5. When x was 3, y was 9, now it's going to be 10. Or in other words, you just put those in and calculate it. Those are my ordered pairs. So 0, 1, I gotta get up to 10. 2, 3, 4, 5, 6. So 0, 1 is right there. 1, 2. 1, 2. I've got 2, 5. And I got 3, 10. So it's just the right-hand side of that base parabola moved up 1. So there's f of x. Domain and range. So domain from left to right starts at 0, goes to infinity. So bracket 0 to infinity. The range, nothing down here. In fact, where the y values start at 1 and then they go to infinity. 1 to infinity. And is it 1 to 1? And you're going to tell me yes. Passes vertical line test, passes horizontal line test. So yes, it is 1 to 1. So that means it has an inverse. So I'm going to go find an inverse. F inverse of x. I don't know its equation, but I don't need to know its equation to get most of the stuff done. Its t-table will be the reverse of this. So 1, 0, 2, 1, 5, 2, 10, 3, etc. So 1, 0, 1, 0, 2, 1, 5, 2, 2, and 10, 3. 10, 3. So this is just sort of the top half of a parabola opening to the right. Here's f inverse. Again, I can see that they are symmetric to y equals x. So I can kind of draw that in and see that happening. If I fold the one over the other on y equals x. I can also talk about the domain and the range of my inverse function. Again, I'm not going to peek over here. I'm just going to look at what I drew. Domain, the x values start at 1 and go to infinity. So bracket 1 to infinity. The range, the y values start at 0 and go to infinity. So 0 to infinity. And so now this is more interesting. What I should see is this range should be that domain, which it is, and this domain should be that range, which it is. So that's good as well. So then the only thing I haven't answered is what the heck is the equation of my inverse function? So to get the equation of the inverse function, so equation of inverse function, I need to take the original function, which says y equals x squared plus 1 with any conditions You need to carry them through, so I need to write that down. And now I'm going to switch. So you switch the x and the y. So this says x equals y squared plus 1. Switch this guy to y greater than or equal to 0. And now solve for y. Solve for y in the main equation. So when I solve this for y, I'm going to subtract 1. So I get x minus 1 equals y squared. To solve it for y, I need to take a square root, and that introduces a plus or a minus. I'm going to write the y first. So y equals plus or minus the square root of x minus 1. But see this condition right here? Because this is implying it's not 1 to 1 anymore, and that's an issue. See that condition? It says y has to be greater than or equal to 0, and this is saying y is plus or minus this. So what is this telling me when I apply this? Apply this condition. Which one of these answers is going away? The negative one, right? So when you apply this condition, you get, so y is actually only equal to the positive square root of x minus 1. So I'm applying that condition, which gets rid of that guy, and this is f inverse. So now I can write f inverse down up here as just the positive square root of x minus 1. And again, a triple check, make sure these fit this. If x is, what did I write? Oh, I was going to say, that's not right. I just wrote, it's square root of x minus 1, sorry. So when x is 1, 1 minus 1 is 0, square root of 0 is 0. When x is 2, 2 minus 1 is 1, square root of 1 is 1. When x is 5, 5 minus 1 is 4, square root of 4 is 2. When x is 10, 10 minus 1 is 9, square root of 9 is 3. Now I feel really good. I got the right answer, and that's the equation for f inverse of x. So inverse functions. So we're going to move on and do a little bit of the next section, which is 6.3. We won't even begin to finish it, but we're going to start it. So 6.3 talks about exponential functions, and I defined it. I said that an exponential function, I swapped out the wrong one over here. I said that an exponential function is a function that looks like this, f of x is equal to a to the x, where a is the base. And notice the unknown, the x is up in the exponent. We've never had that before. We've had x to a power in a function, but we've never actually had the x up here in the exponent. That's what makes it an exponential function. So number one, underneath that, I said, notice the variable is in the exponent. And then I put conditions on the base. I said that a can't equal 1, and a has to be strictly greater than 0. And then I said that gives two options. And I wrote it down algebraically. I said 0 less than a less than 1, or a greater than 1. I'm going to draw a little picture here on a number line to show you what options this is giving us. Again, this is the base. In other words, this is a number here. So for example, f of x equals 2 to the x would be an exponential function, or y equals 2 to the x, or y equals 5 to the x, or y equals 1/2 to the x, where the variable is in the power here. One of the variables, the x, is in the power. And this is the base, which is going to be a number, but I'm restricting the numbers. And I'm saying the number that the base gets to be, for this to be an exponential function, it needs to be, let's see, so here's a number line. It needs to be not 1 and greater than, so here's 0, here's 1. So it can't be 1. So I'm going to put an open circle around 1 to show it can't be 1. And then it has to be greater than 0. So with that spirit in mind, I'll put an open circle here as well. And I'll color all this in, and I'll color all of this in. So instead of parentheses, I'm using open circles here. I'm resorting back to how I used to do it, because it looks a little bit easier to read in this case. So greater than 0, so notice A can't be any negative numbers. It can't be 0, it can be all fractions in between 0 and 1, but then it can't be 1, but then it can be anything from then on. So why are we putting all these restrictions on the base? To keep it what's called an exponential function. So I commented on those in number 2 and number 3. So again, number 1, the comment is, what makes this exponential, first of all, is that the x is in the exponent as opposed to the base. We're used to x to a power, not something to a power of x. The second comment is, why do we have all these restrictions? So let's look at why a can't be 0, and let's look at why a can't be 1, and then let's look at why a can't be negative. So number 2 is talking about why a can't be 0 or 1. So think about this. If a is equal to 1, then what I have here is, I'm going to replace this with y because it's easier to look at. Then y is equal to 1 to the x power, right? If a is 1. But think about this. What's 1 to any power? Even 0. 1 to any power is 1. So this just says y equals 1. This is not an exponential function. This is actually what? This is linear, right? This is the horizontal line where y is equal to 1. So this is linear. This is linear, not exponential. The same thing if a is equal to 0. Then this says y equals 0 to the x power. And 0 to any power except for 0, we won't get into that one. You'll delve into that one in calculus. Is equal to 0, right? 0 squared is 0. 0 to the negative third power is 1 over 0 cubed. Well, you can't do that. So anyway, 0 to any possible power that gives you a real answer is going to be 0. So this basically says, y equals 0, and that's linear, not exponential. Y equals 0, horizontal line on the x-axis. So that's why those two guys are excluded, because they make it not an exponential function, they make it a linear function. Why is it that we've excluded all the negative numbers here? So if a is negative, so for example, then maybe we would have y equals a negative 4 to a power. So I'm letting a be negative, and I put parentheses around it because I want that negative number to have the power on it. And here's the issue with, if a is negative, then we have an issue of imaginary numbers. If x is 1/2, what does the power of 1/2 mean? Square root, right? And what's the square root of a negative? Imaginary numbers. So we're delving into all kinds of problems, and therefore our exponential function isn't really a function anymore, and it has imaginary solutions, and we have all sorts of issues. So then we have imaginary issues. So we get rid of it. So we just let the base be greater than 0, not equal to 1. So basically we're talking about fractions between 0 and 1, and bases that are bigger than 1. So what I would like to do is I would like to look at 2 examples of exponential equation. And it's example 1 and 2. We're just going to look at 1 today. I'd like to look at these and think about their graphs and think about their domain and range, and are they 1 to 1, and do they have an inverse? So all the stuff we just talked about, we're going to do it to these exponential functions as well. And I'm just going to do 2 basic examples from if the a is between 0 and 1, or if the a is bigger than 1. I'm going to do the a bigger than 1 first and see what this graph looks like, and then do all the inverse function stuff on it if I can. So this is example 1. We'll do it and then we'll stop and talk about the test a little bit. So here's my exponential function where the a is bigger than 1. And they want me to graph it. They want me to state its domain and range and decide if it's 1 to 1. And if it is 1 to 1, then I'll be able to think about the domain and range of f inverse and get it graphed and write its equation. So I'm going to do the same setup as I did before. I'm going to think about an xy t-table so that I can get both it and its inverse graphed if it exists, and we'll go from there. So in terms of this, if I just start picking some values here, I could pick x as 0. 2 to the 0 power would give me 1. When x is 1, 2 to the first power would give me 2. When x is 2, 2 to the second power, that's 2 squared, which gives me 4. When x is 3, 2 cubed would give me 8. I'm gonna go negative powers now. So negative 1. So when x is negative 1, that's 2 to the negative 1, which means what? 1 over 2 to the positive 1, so that would be 1/2. When x is negative 2, that would be 2 to the negative 2, which means 1 over 2 squared, so 1/4. Chapter R is going to haunt you. And when x is negative 3, 2 to the negative 3, which would be 1 over 2 cubed, which would be 1/8, etc. So let me graph these. I've got 0, 1. I've got 1, 2. I've got 2, 4. And 3, 8. Uh-oh. See if I can reach. And then I've got negative 1, 1/2. Negative 1, 1/2. So that's about there. Negative 2, 1/4. Well, now I'm closer. Negative 3, 1/8. Now I'm even closer. So what's happening here? As I'm going this way, approaching the x-axis, I'm getting closer and closer, but am I ever going to touch it? Not quite. Even if that were negative 1 billion, I'd have negative 1 over 1 billion. Still not quite, still I'd have 1, I'm sorry. If it were negative 1 billion, I'd have 1 over, well, whatever 2 to the billionth power is. I'd be really close to 0, but never quite hitting it. So what I see going on here is a nice smooth curve that gets very large very quickly and then comes down and gets really, really close to the x-axis, but never quite touches it, which means the x-axis is what? An HA, right? Okay, so let's see. Domain and range. So domain of f of x is negative infinity to positive infinity. And the range of f of x is, I don't start to get y values until 0, but not quite 0, and then all the way to infinity, so parentheses 0 to infinity. Is it 1 to 1? Because if it is, then it has an inverse. Passes vertical line test, passes horizontal line test, so yes, it is 1 to 1, which means it has an inverse. So its inverse function, I don't know its equation, but I know its t-table. Its t-table is going to be 1, 0, 2, 1, 4, 2, 8, 3, 1/2, negative 1, 1/4, negative 2, 1/8, negative 3. I just reverse these guys. Oh, I should comment, you know the expression growing exponentially? That's where it comes from. A graph, an exponential graph that looks like this. It has a base that's bigger than 1, grows exponentially. It increases exponentially. That's what the coronavirus is doing. So here, this guy, I've got 1, 0, and then 2, 1, and 4, 2, and 8, 3, so over here. And then 1/2, negative 1, that would be there. 1/4, negative 2, now I'm closer to the y-axis. 1/8, I'm even closer to the y-axis, so what's happening here is this inverse graph is getting closer and closer to the y-axis. So it also has an HA or VA. So this guy had what? I wanted to write that down. This one had an HA of y equals 0, right? So this one looks like it's going to have a vertical a vertical asymptote of x equals 0. It's never going to quite touch the y-axis. And in fact, let's see, domain range. So domain of the green, the inverse function, 0 to infinity, not including the 0. So parentheses 0 to infinity. The range of the green function, negative infinity to positive infinity. And again, I should see these exchanging with each other, which I do. And this guy, the inverse function, has a vertical asymptote of x equals 0. Look at the exchange. Again, vertical, horizontal, y, and x equals 0. The only thing I need to do here is think about the equation now of this inverse function. So I go to the equation of f inverse. So I take the original function, y equals 2 to the x. There's no restrictions or anything. I exchange x and y. So I get x equals 2 to the y. And then I solve for y. Well, look at where the y is. It's up in the exponent. We haven't learned anything that tells us how to solve this. So I'm going to have to think about that one. We'll figure it out later. So that's as far as I'm going to go in terms of content. So we didn't finish 6.3, we just did the first example. I want to make a few quick comments about the test. See if I can find them. So in terms of this test, again, you should have gotten the email detailing deadlines and when things are going to happen and what you should be doing. In terms of the test itself, the quiz that you took, know how to do it. Okay, if it was on the quiz, it could be on the test again. So I would review it. In terms of chapter 5, 5.1 and 5.2 go together and they get you ready to graph a polynomial equation or function, and you're going to need to know how to graph a polynomial function. In other words, you need to know how to find end behavior, how to find zeros and their multiplicity, and therefore what's the behavior at each zero and how to graph that. You're going to have to know how to find ordered pairs in between in each interval so that you get a nice looking graph, a nice smooth graph. 5.3, all the examples in the handout, make sure you know how to do them. 5.3 and 5.4, this is graphing the rational function and answering the questions that go with it. In other words, what's the domain and therefore what would be the vertical asymptotes, the horizontal or the oblique asymptote, knowing how to figure those out, how to get them graphed, knowing how to find the intercepts, the y-intercept, and then the zeros and the behavior at the zeros again, and graph them, and then knowing how to find the ordered pairs that you need to find in each interval on the rational function as well to get that rational functions equation completely graphed accurately. The examples I gave you on the handout, all of them are my favorites. Make sure you know how to do them. In terms of 5.5, where you were solving rational and polynomial inequalities, I think there were 4 examples. Make sure you know how to do them. Make sure you know how to find the critical values and what to do with them in terms of test points. And then 5.6 and 5.7, they kind of go together, basically understanding how to find all the possible rational zeros and then how to actually find the zeros based on that by doing synthetic division and trying to get the function factored linearly. So do not leave a factor that is not linear. So if you end up with an x squared plus 4, you need to keep factoring that. And we talked about how to do that in those 2 sections. And in addition to that, understanding complex zeros or imaginary zeros and what that means and how you can factor when there's imaginary zeros and how you can solve when there are imaginary zeros, etc. All the examples on 5.6 and 5.7's handout, I don't have favorites. You need to know how to do them. So that's my only comments about these 2 chapters. I wish you luck. Be looking for that email that has your test attached on Thursday. Do not contact or talk to other students in the class when you're taking the test. You're taking it by yourself with your TI-30XIIS by your side and a pencil and the test printed out, or if you can't print it out, then the work done on each piece of paper. You need to show all your work. Do not do not converse with other students. If you have an issue, you take it up with me. And please email me by way of Canvas. That's the system I'll be on, and that's the one I'll be looking at if there are issues. So good luck, and I will be in contact with you on Thursday and after that. Have a good one.